on stage 𝗂𝗽𝗱𝗁𝗂𝗁𝗁. So she is R&D manager at 𝗂𝗽𝗱𝗁𝗁 Systemics, and she is managing the methodology roadmap for the association. And so, Carla, I will let you introduce the methodology.
Yes, thank you. Thank you very much, Nicolas. So, hello, everybody. I will be presenting very quickly. This is very much a teaser on the end-to-end methodology within the European Trustworthy AI Association. So just as an introduction, we have all of these concepts around AI trustworthiness, so explainability, fairness, accountability, and many others. We also have the structure that was provided by the key 7 key requirements from the European Commission. We have the AI Act, we have the standards that are to come, but we also have a lot of international initiatives fostering sharing and consensus on good practices. One of the examples is Responsible AI UK. And the reason I'm bringing this up is because I would like to highlight something that we wrote in this white paper, and it is the fact that we have now many toolkits, frameworks, guidance documents. We don't necessarily see, this is a paradox, we don't necessarily see an accelerated adoption for more responsible or trustworthy, in this case, AI. So the notion of how to operationalize these concepts is key. And it is part of what we're going to tackle today, how to do this in the development cycle. And this is what we push as the idea of trustworthy AI engineering at a system level, of course. So on that note, the end-to-end method that I will give a brief glimpse of weaves these concepts and requirements together in a coherent manner within the entire development cycle, and very much focused on a system that contains AI components. So not focused on AI components in an isolated manner, and it limits overriding and disrupting what already exists, what we know that already works in the industrial processes today. So what we do today, what we want to do today is to boost developments and to enrich the method through collaboration with industry and with academia. For those of you who already know the method, bear with me for a few minutes. For those of you who don't, this is the general view of the end-to-end methodology. I want to say that this is a result of years of collaboration between several sectors in industry. It is an evolving work, so this continues to grow. It is very much cross-sector, so we have players from the aerospace industry, we have the automotive industry, we have people from AI, people from safety, security, and so on. And as you can see from a very high level, behind each of these phases, you have entire pipelines, but from a very high level view, it is based on the V cycle development that we know in software engineering and in systems engineering. The premise, if I want to give you a takeaway on this, the premise is that trustworthiness is to be assessed from end to end in the entire development process for the entire system. And the why including AI needs to be able to be traced in the entire flow. And this way we're going to be able to have assurance cases at the end of our development. So we start from the system and then we go down to very specific phases that have to do with the integration now of AI components. In that sense, the impacts that we can have from such a method are technical, but also organizational. On the technical level, of course, we're going to be able to monitor better the performance of whatever it is that we're producing at a system level, and also the AI components in there. We're going to have traceability, we're going to have systematic risk mitigation, consistency, and very importantly, integrated testing strategies, because we're going to be defining the requirements that we're going to be able to verify at the end of the cycle. In terms of the organizational transformation, what I wanted to mention is that Perimeters are going to be more specific to the teams. So take, for example, a data engineer that specifies, produces, and evaluates data sets. Its role is very much contained in that perimeter. And this is not the perimeter of an ML algorithm engineer. The ML algorithm engineer will give the constraints, the requirements to the data engineer, and they will iterate in terms of what can be done in terms of data generation and what cannot be done. In the same logic, the data engineer is going to be interacting with other phases of the entire methodology. So it's going to be interacting with people from security, from safety, from human factors, and he's going to be receiving requirements from higher phases, such as the intended purpose of the system, operational context, and so on and so on. So on that note, there's a lot that has to be done in the method. There is a lot going on still. What we want to do is to boost innovation through collaboration. We need new use cases, new AI types to be evaluated, some phases that need to be completed. And if you will allow me, I will describe some of the pillars for the method. If we start by the notion of ODD, it is the operational design domain. This is a concept that is very well known in the automotive industry. It's the conditions, the operating conditions under which a given driving automation system is specifically designed to function. Outside of these conditions, we cannot guarantee the proper functioning of the system. This is something that is very well known in the automotive industry, and we want to transpose it into AI-based systems. In that sense, what we want to insist on, if we want to ensure trustworthiness, is that when we are building systems that have AI in them, the operational design domain cannot be the domain covered by the distribution of the training data. This is not trustworthy enough. Proper formal ODD needs to be specified for the entire system, and based on that, we need to derive the premises that we need to derive the requirements that are going to guide the development of all of the components inside that system that will be coherent with the intended purpose of the system. This is just an example for the ODD in the automotive industry. In the case of this function, the ODD is the speed ranges, the traffic conditions, weather, and so on and so on. And the goal is to drive the development of AI-based systems with this premise in mind. So in this sense, the ODD is very much a pillar in the entire workflow. And just to give you a glimpse on the method, what you have behind this phase is something like this. So you have entire pipelines of the activities that need to be carried out, the perimeters, who does what, what's the flow of information, what are the sub-activities, and so on and so on. You can you can actually go and go see these results. And again, this is very much a work that is evolving today. To wrap up, I'm going to address the rum methodology, which is another pillar that we want to keep around the end-to-end methodology. So to keep it simple, the premise of the rum methodology is to treat robustness, uncertainty quantification, and monitoring as a whole, as an entity, as indivisible. And the thing is that when we are measuring, when we are providing a value for robustness in a given situation, we need to be sure of the uncertainty that this value carries and the nature of this uncertainty. How can we make it better? How can we know if we are overestimating the robustness in some sense? And to that end, monitoring is fundamental. So I'm giving some references. And just to wrap up in the sense, there is an entire mathematical background behind this methodology. This methodology could help characterizing different ODD zones to better detect possible failure modes. So this is where we are going to. It could be able to help us assess potential trade-offs at system design and many others. And so today, RUM is considered as part of the roadmap to be able to enrich the end-to-end methodology. We have some research projects that are right now working on this, and there is some future work that is already envisaged to be able to do this integration. Now, if you will allow me, I will give the floor to our next speaker. Not before I say that if you have any questions, if you want to know more about the methodology, do not hesitate to reach out to us. So now we're going to go to assurance cases and how to provide the idea of how to provide the justification necessary to ensure the trust that we can have in an ML-based system and how to trust this argumentation. Thank you. Thank you all.
Okay, Eric, I think you could join the session. So over to you for the presentation of the assurance cases.
Okay, thank you. Good afternoon or good evening or even possibly good night to everybody. So I am 𝗂𝘁𝘁𝗿𝗂 from RIT 𝗂𝘀𝘂𝗃𝗁 in Toulouse. And in this presentation, I will give you a rapid overview of the concept of assurance cases, the role they play in reaching the objective of confidence, and I will give you a rapid overview of the tools that we have developed to support this approach. But first, I would like to start from the very beginning and to give some meaning to the concept of dependable system and dependability. And a dependable system is a system on which you can rely, and to rely on these systems, you need some. You do not rely on faith. You need the facts, and you need to reasoning. You need some evidences. So you need something which relates to reason, and this reliance or this confidence can come from the standards or from a positive track record. But in the case of AI, we are far from having a complete standards, and we are far from having a track record. So we need something else. So in order to have something on which we can base our confidence, we want to have some clear and explicit argumentation relying on claims, on evidences, and the relation between all these elements must be clearly stated. Often and usually, our reasoning is implicit. So we are rational people, so we reason. But this is never written anywhere. And the purpose of the assurance cases is to put this reasoning on a sheet of paper so that it can be criticized, it can be validated by someone else than yourself. This is what an assurance case looks like. You have a claim. For instance, in that case, we have the statement that the trained ML system is robust, and the argumentation relies on the fact that some property P1, P2, or Pn are satisfied, and if these properties are satisfied, then the trained ML system is considered robust. Yes. And so you have to ensure that property P1, P2, and Pn are satisfied, and you have to provide evidences that these properties are satisfied. So here you have the three main concepts: the claim, the argument, and the evidences. This is another representation of the same reasoning tree, but using a standard representation called GSN, and you see exactly the same elements that I've shown before. What is important to see here that in a given context, something may be an evidence, and in other contexts, this evidence must be becomes a claim and must be refined in the same way as we've seen before. So an evidence is something which is consensual for someone. It may be an evidence for someone else. You may have to provide a complete reasoning tree. So in the Confidence.ai project, we have developed both a set of argumentation patterns, so predefined reasoning trees, and a tool to support the building of these trees and to make explicit the relation between the engineering elements and these claims, and then the complete reasoning tree. So in this diagram, we see that we start from an activity. So this is typically the kind of activities you will see on that have been briefly presented by Carla before. And we have an activity that produces some item. An item may be a trained ML model. And this item is selected at a given point in time. We identify the properties that this item must satisfy. So this is the second point. Then once we have identified the property, we select the relevant generic argumentation, so the trees that I've shown before. And we adapt this generic argumentation because the argumentation covers all the cases, all the context. And it may be the case, and I will give you a brief example afterwards, that in a certain context, a certain method can be applied, and in other contexts, another method must be applied because the practices are not the same or the conditions are not the same. So you have to tweak the argumentation, and the tools allows to do that. And once you have identified your own argumentation, which ends by some evidences, you have to provide these evidences, and to provide them, you have to perform some activities, and those activities will be re-injected into the workflow, the previous workflow, which was not containing this specific activity, which is related to VNV. And then you may use the same artifacts to build a VNV plan, or at least the outline for a VNV plan. Of course, having a reasoning written on a sheet of paper does not ensure or guarantee that the system is correct. You have also to ensure that the reasoning is correct. So you have the kind of meta reasoning to be applied. And we have also worked on that topic, but I won't go into details about that today. So let's take an example. Here you have a piece of the workflow. In this workflow, we produce some engineering item. Here, the engineering item is a trained ML model. This trained ML model must comply with here 3 properties. It must be robust, it must be fair, it must be explainable. Let's take the property of robustness, and once we have selected it, we will take the generic argumentation related to robustness. And here is an example of what it looks like. It's very difficult to read. It's impossible to read, actually, but you will see on the next slide a closer view of the argumentation. But here, what we can see, we can see the reasoning tree with 2 main parts. And for this property, one part is related to a certain choice of a distance to express the robustness. So either the L2 distance or the L infinite distance. And depending on your choice, on your the meaning you give to robustness, so the choice of the distance that you have done, you will either take one part of the argumentation or the other part. So this is what I call the genericity. Here, the argumentation covers both, and in a certain context, you will choose either the left one or the right one. So here we have a closer view to this very specific argumentation about robustness. So it's just a part of it. It's much bigger than that. But what we can see more or less here is that we rely on, here in this specific case, we rely on academic work which supports the different alternatives to demonstrate robustness. Robustness may be demonstrated in different ways. The confidence you may have on certain method may depend. So you may either choose this one, the first one, the second one, the third one, or the fourth one, or possibly a subset of them, and provide the evidences related to each of the methods that you've chosen. And in this specific case, we have the reference to the paper that support the demonstration of robustness. So if we come back to the overall argumentation tree, if we focus on the left part, we can see that there is another case where 2 different strategies may be applied. You may verify robustness using a process-based strategy. You ensure by construction that the property will be certified. And on the right hand, you will verify afterwards, once you have built your system, that it is actually robust. So this is clearly a strategy. You may take one or the other, or possibly both. And in practice, using the tool that we've developed based on 𝘂𝘱𝗂𝘁𝗂𝘁, you will select a strategy among those that are available, and you will obtain, as a result, you will obtain the appropriate argumentation tree where all the parts that are not relevant with respect to your choice have been removed. So in that case, here we have simply removed the right part of the argumentation. And the next step, which is performed automatically, is the injection of the activity within the initial workflow. So we can do that. So here we have done a certain choice. You may do the opposite choice, and you will get another tree and another workflow. And you may possibly select both, and you will get the complete picture where we'll have both strategy by design or strategy by evaluation or verification. So the key takeaway from this work is, first, confidence must be based on some explicit reasoning, especially with AI, which is both new, complex. And if we rely on, if we consider that is a good approach, we have to expose the claims, the argument, and the evidences using the formalism of assurance cases. And toward that goals, we have built a tool that allows to model the tree, to capture the ML workflow, to capture the relation between the workflow engineering items, the items produced by this workflow, the properties, and the argumentation tree. And we have also developed a pretty small number of generic argumentation, and this is something, a work which must be further developed. That's it. Thank you. If you have any question, maybe later on.